The Gradle Summit 2017 is a fantastic place to learn how you can improve developer productivity with state-of-the-art build infrastructure. That's why we're here. And we're all on a journey to improve developer productivity, right, in the various functions we have. It mostly has been a journey in rough waters so far. Right? For a few daring organizations, it has been a massive pioneering effort to solve problems that have never been solved before. But for the majority of the organizations, it was just about keeping a ship somehow afloat, while teams and code bases are growing and the software stacks are more complex than ever. So afloat means to somehow enable the shipping of software, but with a low developer productivity. Many organizations and teams are still struggling to get the basics right, but even in the best organizations, productivity is still far from where it could be. So what makes this a particularly interesting situation is that the economic impact of low developer productivity is enormous. So we are doing many ROI exercises now with customers by using the data they have collected with Gradle Enterprise. One typical data point we got from a 600 people team is that for them, a minute of faster build time means $1.6 million per year in savings, just by developers spending less time on waiting for a build. What if the build is 5 minutes faster? What about the additional savings of faster CI builds, of shipping software faster, of developers staying more in the flow, of developers debugging faster, of happier developers? The list goes on and on. So why are we not investing like crazy to harvest returns like that? Only a few organizations do that at this point. Well, many organizations are too busy with keeping the ship afloat to think about the bigger picture. Then we don't usually measure those inefficiencies to put a dollar amount to them. We got used to them. And finally, and most importantly, it was very difficult to improve the situation substantially with the technology that has been available. But there is gold to mine. And I'm excited that with Gradle 4.0 and Gradle Enterprise, we dug a tunnel for you. It's a breakthrough. Massive improvements in developer productivity are now within reach for every organization. The mines are everywhere full of gold. Everyone is still far away from the point of diminishing returns when it comes to investing into developer productivity. So why is the build infrastructure key for mining this gold? So developer productivity has obviously many dimensions, right? Your IDE, your languages and frameworks you're using, training, the food in the cafeteria. But most organizations make good choices in those areas nowadays, definitely here in the Bay Area. Today's area of big impact when it comes to developer productivity are the following, right? It's the speed of feedback cycles, it's the degree of automation, it's the time it takes developers to debug the problem, and it's the productivity culture. In all those areas, Gradle can help you to get much better. Let's start with the first very important one, speed of feedback cycles. To truly realize fast feedback cycles for your organization and keep them fast, several things have to happen. I will talk about all of them in detail. Let's start with maximum build performance. What is this? Maximum build performance is the maximum achievable performance of a build system for your code base. So the maximum build performance is a quality of the build system in the context of your code base and the way your code base is structured. When the maximum build performance is low, there is no goal to mine. The goal is not accessible. Maximum build performance is the foundation for fast feedback cycles. You will need more than just good maximum build performance to be successful. We will talk about that soon. But without it, there's not much you can do. So Gradle has added from the very beginning features to provide a better maximum build performance with up-to-date checking, compiler daemons, some form of parallelism, and quite a few more features. Those were significant improvements compared to the competition, but no game changers. The Android situation was different for a variety of reasons. The good news is that over the last 12 months, Gradle's maximum build performance across project types has been drastically improved in general, and specifically for Java and Android. Gradle is now outperforming some of its competitors by 2 orders of magnitude. It provides the highest average maximum build performance of all build systems that are available, at least for the builds we are involved with, and those are quite a few. The performance has improved in many areas. It was a very holistic effort on our side. So for example, much faster up-to-date checking, less memory consumption, faster startup and configuration time. But there are key areas of improvement that really changed the game. One thing to keep in mind is that the structure of your code base determines which features are having the most impact on maximum build performance. We have an interesting example for that. So we invested a lot of time to make dependency resolution faster. Not just when downloading, but also when everything is resolved from the cache. All our users will enjoy the speed improvements coming from that, but for some it is essential. Take Netflix, for example. They have structured their code base into many repositories, and the repositories integrate via binaries. Let's look at the impact of faster dependency resolution on one of their important projects. With Gradle 3.4, the build time was 13 minutes. With Gradle 4.0, it went down to 2 minutes, almost solely because of faster dependency resolution. The maximum build performance is heavily determined here by the speed of dependency resolution, as the project has a huge dependency graph, many dynamic dependencies that updates very often. Who would have thought? So here's what we did to make dependency resolution faster. So when you have exclude rules in your build, they're now handled much more efficiently. When you run builds in parallel, the locking of the dependency cache is now more performant. And finally, Gradle now downloads artifacts and metadata files in parallel, also when -- parallel is not enabled. Thank you, Netflix, for partnering with us to improve this. Those partnerships are extremely beneficial for the whole Gradle community. Adam will talk in a few minutes how variant-aware dependency management has enabled much faster Android builds. That's another very interesting topic. OK, so maximum build performance for a given code base cannot be expressed by just one number. There are multiple numbers corresponding to different use cases. A very important use case is doing a recompile or retest after changing a few lines of code in your code base. For example, when a developer is debugging a service or an app, then changes something, wants to see the change in action, does another change, and so on. Let's look at the number of different types of Java projects when doing a recompile and compare this with Maven, which has no support for incremental builds. So for a large monolithic app with 50,000 source files, that's pretty big, Gradle compiles 10 times faster than Maven after one line of code has changed. Gradle uses its incremental compile capability. You see there is some overhead in analyzing the huge dependency graph between the classes, but it's well worth it. For a very small multi-project build with 10 sub-projects and 50 source files per project, Gradle is 8 times faster by using incremental compile and compile avoidance. For a medium multi-project build with 100 sub-projects and 100 source files per project, Gradle is 42 times faster. 2 seconds versus 1 minute and 16 seconds. And that's interesting. So when we talk with organizations that have many of those kinds of medium-sized repositories, they often say build time is not a problem for them. What does it mean it is not a problem? It means developers are not complaining. But we learn at the beginning of this keynote what 1 minute of build time improvements can mean in financial terms. And having many small repos means having many of those builds, right? So even if it's not perceived as a problem, it's a huge opportunity. And grasping this opportunity will turn this into a problem for your competitors. For a large multi-project build with 500 sub-projects and 100 source files per project, Maven takes 380 seconds to recompile, Gradle 3.7 seconds. So this means 4 seconds versus 6.5 minutes. It's 100 times faster. It changes fundamentally the way you can work with such a build. The folks from Mutual of Omaha were so kind to share the following story with me. So people get used to slow build times, right? And they learn how to distract themselves while the build is running. When Mutual of Omaha introduced pair programming, the distraction mechanisms the people used, checking emails or reading about the NBA finals, didn't work anymore. This waiting time became really awkward when there were two people sitting in front of the computer waiting for the next step to take. And people in this setting fully realized the waste that slow builds are causing and how inefficient collaboration is with such slow feedback cycles. Pairing is a nice awareness exercise for that. So let's look at build times for Android. Those numbers were already presented at other events. I'm still very excited to talk about them. The numbers we will see are for a very large Android test project when rebuilding a single variant. With Android plugin 2.2 and Gradle 2.14.1, a rebuild from scratch takes 6 minutes. With Bug, an Android build system from Facebook, this takes 80 seconds, so it's 4 to 5 times faster. With Android plugin 2.3 and Gradle 3.4, this takes 90 seconds, and with 3.0 Alpha 4 and Gradle 4.0, this is down to 80 seconds. When we change a single line of code that changes the ABI, the public interface of a class, with Android plugin 2.2, this takes 210 seconds. With Bug, this takes 26 seconds, so 8 times faster. With Android plugin 2.3, it's down to 37 seconds. With 3.0 Alpha 4, it's at 25 seconds, which is the best number. For a non-ABI change, for example, a change in a method body, we have 210 seconds, 70 seconds, 37 seconds, 8 seconds, which is again the best number, and it's 26 times faster than with Android plugin 2.2. Once we have incremental compile with annotation processors working, both the ABI change and non-ABI change scenario will be faster again. There are other significant features that are work in progress, which will significantly affect positively the Gradle performance for all scenarios on this chart. You have the ultimate experts at this conference. In their talks, we will get into much more detail. These test projects represent a corner case with 135 submodules where the code is evenly distributed across all modules. It does not reflect the reality of 99.9% of the Android projects out there. It is good to have such a corner case. Gradle is now the fastest build tool for this test project. For typical Android projects that have larger modules where the code is not evenly distributed, the performance advantage of Gradle over a tool like Bug is even more significant. But it's definitely much more interesting to look at numbers from real-world projects that reflect the reality of typical Android projects better. Let's look at the Twitter Android app. For Twitter, the time it takes to rebuild a variant for the Android app when doing a non-ABI change went down from 3 minutes and 30 seconds, roughly, to 13 seconds, right, with 3.0 Alpha 4. And we are very confident that we will get this down even further. I'm delighted that Cesar and his team from Twitter are presenting here at the Gradle Summit on what they have done to get there. One of the Gradle highlights of this year is the support for caching build output over time. This output can be anything: compiled classes, generated sources, test results, documentation. The effect that has on build time is tremendous for local as well as for CI builds, for clean as well as non-clean builds. Let's look at the number for Java projects when we run clean builds that compile and run the tests. We used the same type of projects than for the incremental build performance chart on the previous slide. For a large monolithic app, the number is 282 seconds with Maven. For Gradle 4.0, we're not using the cache. Just a plain clean build, it's 146 seconds. This shows you how efficient Gradle 4.0 is, even without using any caching or build avoidance. We have invested a lot into this area. Just the pure mechanics are so much more efficient now. When using the build cache, the build time is now 16 seconds with Gradle, so 18 times faster than Maven. For a small multi-project build, the numbers are 23 seconds, 13 seconds, and 0.62 seconds with the cache. For a large multi-module build, for a medium multi-project build, it is 283 seconds, 79.3 seconds, and 3.6 seconds. So 4 minutes and 45 seconds to 3.6 seconds. For a large multi-module build, this is 18 minutes with Maven, 6 minutes with Gradle and no cache, so 3 times faster. And it is 19 seconds when the cache is used. 19 seconds compared to 18 minutes. You might argue that fully cached builds are rare. They happen. For example, when a developer updates from version control in the morning and needs to regenerate the generated sources to work in the IDE. but most builds will not be fully cached, definitely not on CI. But if the change is in a peripheral project, for example, on which no other project depends on, the actual build time might not be 19 seconds, but let's say 22 seconds. I take that. And the faster the CI builds are, the less changes they need to build, hence the more effective the cache will be. Your average time savings will be very significant. This is a tweet from Fedor Korotkov, who made a large Gradle build at Airbnb cacheable. The graph shows the average CI build time after the cache has been enabled. The performance improved within hours by a factor of 4. And they have quite a bit of Scala in the code base, which is not cacheable yet with Gradle. So there's more to come. If you have any questions about this, Fedor is here today, as well as other members of the Airbnb build team. I'm sure they will are happy to talk with you. What about the Gradle build cache for Android? So some tasks are already cacheable, but it's still experimental. There's still some optimizations we need to do. The cache will only be supported in the Android plugin 3.0 stream. Right? So if you're not on 3.0, you will not be able to use the cache. For clean builds, we already see 50% performance improvements, definitely more to come. The plan is to have caching for Android production ready with the final release of Android plugin 3.0. Gradle 4.0 ships with a local cache out of the box. The local cache is not enabled yet by default. Once the cache API is fully stable, it will be enabled by default, probably in 4.2, maybe in 4.3. But the Gradle cache, as most of you know, also supports now remote cache backends to share build outputs across machines. Gradle Enterprise provides such a cache backend. Luke is leading this effort and will show us the latest features.
Thank you, Hans. Camera switched over, please. All right, thank you. Yes, thank you, Hans. What I'd like to show now is just a very simple contrived Gradle build I have here. In a second. Here we go. All right, here we are. OK, so I have a Gradle build here. I'm running with clean. I'm going to be running with clean here just to negate Gradle's incremental build. And you can see that there's about 5 tasks in this build. They took about a second each. Of course, if I run this again, Gradle's going to have to redo all that work. I'm running with clean here, so I'm not getting incremental build. Now, of course, you don't run with clean for every build, but Hans pointed out some of the scenarios just a second ago where build cache is effective, such as coming in the morning, checking out, getting the work from overnight, and various other scenarios. So if I run that same build by adding -- build cache, which is how I enable build cache for a Gradle build, as I'm running this for the first time, the same thing happens. Gradle goes through all that work. But of course, now if I run it again, instead of taking 5 seconds, it's now less than 1 second. So what's happened here is I'm using Gradle 4.0 here, and I'm using the inbuilt local build cache. So in between those invocations, Gradle has squirreled all that output away, pushed it to the cache, and now it's bringing it back. So the build cache comes with Gradle out of the box, the local build cache. What I'd also like to show is the remote build cache that ships with Gradle Enterprise. So here I'm in the settings file of my build, and I'm just going to turn the local cache off so I can just use the remote cache for the sake of demonstration. But you can, of course, use both. Use a local cache and then use a remote cache, which will pull from if you don't have these things in your local cache. So here I'm going to enable the remote cache using the built-in HTTP cache connector shipped with Gradle. And I have this incorrectly set up. And what I also have is an instance of Gradle Enterprise running at this address. And Gradle Enterprise ships with a remote build cache out of the box at /cache of the install. So now I've changed this to use a remote build cache. And if I run this again now, I already have those. I didn't save that file. So I run it again. That remote cache is empty. So I'm running it again. It's running those tasks. It's pushing the outputs up to that remote cache. And of course, I run it again. It now pulled those artifacts from that remote cache, and it was much, much faster. So that's just a, here is the Gradle Enterprise installation running on, it's a little bit hard to see there. I can't make that bigger, sorry. But This is just running on an AWS box. It's something we've installed there. It's very simple to install, and it comes with the build cache implementation out of the box. Here's /cache was where we went to for the actual cache implementation here. Well, that same application, I have cache admin here, which is the administration application of the cache. And what I see here is just some breakdown of the activity that's happened with this cache. We've had this up for a few days, testing it out, and you can see what's going on in terms of hits, misses, hit rates, data in and out, etc., for different windows. So we shipped the building cache with Gradle, Gradle Enterprise 2017.3, and earlier this week we released Gradle Enterprise 2017.4. And what 2017.4 also brings is the ability to install and run multiple cache nodes. So here I'm on another AWS machine, and we distribute the build cache node as a Docker image. So on any machine that's Docker enabled, this is just a plain AWS EC2 instance. The build cache node image is available in the public Docker repository, so this command will work on any machine that is Docker enabled. So that will fetch that image, run it up, and this is now running at here. So this is the build cache node software, and build cache nodes connect back to Gradle Enterprise. So from Gradle Enterprise, I can go and provision multiple nodes here, and then configure those nodes with the appropriate configuration, and they talk back there. So now this is actually a fully usable cache. So similarly, first run, that cache is clean. Gradle does the work locally. It's pushing those artifacts up to there and pulling them from that remote cache now. So that software is actually available today. If you want to try out build caching and remote build caching, you can install the build cache node software on any machine. You actually don't need Gradle Enterprise to use it. It works standalone. But if you connect it up to Gradle Enterprise, you can administer certain aspects of it, change how much storage it uses, the maximum size it will accept, configure authentication for it, have a look at its activity and various things. So it can be centrally monitored and configured from Gradle Enterprise. Thank you very much.
Thanks, Luke. Yeah, and I guess you can learn more about that in your talk about Gradle Enterprise. OK. Gradle for O has much improved support for build parallelism. This is a very important feature to increase the Gradle maximum build performance further. We call it the new Worker API, and I'm absolutely thrilled about those new capabilities. So please welcome Gary, one of the lead engineers of these features, to demonstrate it. Yeah, so this new Worker API will eventually replace the current parallel mechanism that you can enable with --parallel. Who of you is using --parallel for the Gradle builds? So, and you can see it's 20%, right? 30%, not more, right? And for various reasons, and one is that it's not enabled by default. In any case, the expert can talk much better about that than I can. Okay.
There it goes, yeah.
Thank you, Hans. Okay. So let's talk a little bit about the Gradle Worker API. And I have limited time up here, so let's just get down to brass tacks. What's in it for you? Why would you want to use the Worker API? So the first possible way that you might want to use the Worker API is if you have builds where you're using Java exec and calling it over and over and over again to use an external, some sort of external library. With the Worker API, you have the ability to use what we call worker daemons. And worker daemons are long-lived processes. They keep your classes warm. The class loaders are warm. And instead of calling out and spawning an additional process every time you need to do a unit of work, with the worker daemon, this process stays alive. You just simply send requests over to it to do that work. But it goes beyond just being able to replace Java exec. What it really is about is maximizing the resources that you have on your system. We pay a lot for CPUs with multiple cores. We should use them. And so with the Worker API, what I can do is I can run units of work inside the process by spawning them in threads within the process. And so instead of having a single-threaded task execution, I can break up my work into multiple units of work, these immutable units, that I can then submit into the worker executor. And this worker executor will now run all that stuff in parallel and will finish the work of our task much more quickly. Now, it goes even beyond improving the performance of a single task. The Worker API also enables what we call parallelism by default. And with parallelism by default, what this means is that if I have a task that's broken up all of its work into these immutable work items and then has submitted them to be executed, and all this task is doing is now waiting on that work to complete, well, if we have -- parallel, we have this ability to do inter-project parallelization. So multiple tasks in multiple projects can run in parallel. But with the Worker API, I can go to intra-project parallelization. So if this task is waiting for work to complete, I can potentially select another task from the same project and start executing the work for that task. Now, once he submits all of the work that he wants to complete, I can start more tasks. And what this ultimately ends up doing is that I can start queuing up work, and the only thing that constrains my ability to get this work done are the resources available to me, and not just the single-threaded task execution. Okay, so what I'm going to do is I'm going to show you a demo of the Worker API in action. And so in this demo, what we're going to do is we're going to process WSDL files. We're going to convert WSDL files from XML and to generated Java source. And we're going to do this on a number of different WSDL files. And so each WSDL file that we process in our initial implementation is going to use Java exec. And so Java exec is pretty simple. I would pass in a main class that is this WS import class. I would pass in a class path that's associated with that. And then I'd also pass in a WSDL and some arguments that might be associated with that WSDL. Now, to convert this over to the Worker API, it's fairly simple. I'm going to do something here where I submit a unit of work to the worker executor. And instead of specifying a main class, what I specify is this per unit of work implementation class, this WS import runnable. And I'm going to show you what that looks like in a second. But I pass this in, and then I provide a configuration for this unit of work. That configuration would, number one, be the isolation mode. And I have a couple of different isolation modes that I can select. One is isolation mode.process. So the process isolation says I want to execute this unit of work in a completely separate process. And that completely separate process could have potentially different environment variables, different system properties. It could potentially even be using a different Java executable. And then I also pass in my class path. Oh, I'm sorry. Going back to the isolation modes, another isolation mode is class loader, which means that I want to run this work not in a separate process, but I want to run it in process in another thread, but with an isolated class loader. And then the third possible isolation mode I could have is none, which says I want to run this in process, but with in another thread, but with the same class loader that my task is using. Then I also pass in the class path, just the same as I did with the Java exec. And then I'm also going to configure these parameters, which are the same as what I was using with Java exec. Now, these parameters are going to end up being constructor parameters for my per unit implementation of work, this WS import runnable. Which, if we take a look at this is fairly simple. All it is a constructor that takes my arguments to process my WSDL file, and then the run method is the actual implementation of this, where he's going to use this WS import tool from the WS import libraries. And so what we see is that converting from, say, a Java exec to a worker API implementation is fairly simple. And so now what I want to do is show you this in action. And so what you're going to see in this demo are 3 different builds running concurrently. One build is using the initial Java exec implementation, so he's spawning Java exec every time to process a WSDL. The one in the middle that you'll see is the implementation using worker daemon, so he's running this work in a separate process, but using the worker API. And then the third build that you'll see, which will be the build on the right, is going to be the same work being done, but using worker threads with an isolated class loader. So let's take a look at this. And so what you should see initially here, or immediately recognize, is that we're starting to see some of that parallelism by default on the 2 that are using the worker process, or the worker API. And we're running tasks within the same process at the, in parallel. If we look at the amount of time that it took, for Java exec, this was 14 seconds. With worker processes, it was 8 seconds. And with worker threads, it was only 5 seconds. So we cut it in half with worker daemons, still spawning extra processes. But then when we went down to threads, we cut it by 2/3. OK, so if you want to learn more about the worker API, come to my talk later today. Myself and my colleague, Paul Merlin, will talk about some of the types of problems that the worker API can solve, as well as going into more depth on how to implement it. Thank you.
Expect for the second half of the year. Here's some of the features that are on our roadmap. So the worker API is part of 4.0, but what we haven't implemented yet is that the Gradle core plugins and the Android plugin will make full use of the new worker API. Right? So for example, the Gradle Java plugin is not using yet the worker API to have better parallelism. That is work we're going to do, and that will have a very nice effect on your build performance. And it will be enabled by default. No -- parallel, right? Whenever you have multiple processors, we will use that. I already mentioned that. Incremental compile with annotation processors. We're working with the Google Android team to enable that. This is particularly relevant for the Android community, as Android Studio has the deep Gradle integration, and for very incremental Android workflows, right? This is now often the bottleneck, right? The Java C time. It's good that we have reached that point. Now we want to make the next step that Java C also gets very fast for projects using annotation processors. But also many Java projects will benefit from that, obviously. I'll also mention that Scala and C++ tasks are not cacheable yet. That's something we will be working on. Hello, configuration time, my old friend. Still not 0, huh? Well, a lot has happened. For large Android projects, we, together with the Google Android team, got it down by a factor of 200. That's not too bad. We substantially improved it for Java projects, but the maximum configuration time is still too high for very large projects. It takes people out of their flow. It prevents people from adding generic automation tasks to their very large Gradle builds, which is a shame. So we know what to do. There were higher performance priorities with the features you have seen so far, but we will now finally tackle this. For the build cache, we will allow for n-level caches. So for example, to use S3 or Google Cloud Storage as a L2 cache, and have L1 caches, for example, the Gradle Enterprise cache nodes, in closer proximity to your teams, who will then also implement access control and other additional services. We plan to provide multi-location support for the Gradle Enterprise cache backend that will include smart replication mechanisms. And finally, we want to make the cache bandwidth aware, so that when a person is working from home with a slow connection, Gradle will automatically build certain output locally if it will take longer to retrieve it from the cache. There's more stuff that might come, but this is something we're pretty confident we will deliver. So, still have some space potentially for additional features. As you have seen, the maximum build performance you can achieve now with Gradle is impressive, and it will get even better. How can you get your actual build performance close to the maximum one and keep it there? Your project is growing, embracing continuously new technologies and frameworks. Your build logic is evolving. Your project is undergoing organizational changes, opening up new locations. If you don't invest into continuously optimizing your actual build performance, it will definitely regress or never even get where it should be. We see this all the time. And with all the new mechanisms that improve the maximum build performance, there is fortunately more to optimize. By looking at build data from companies, we find surprising inefficiencies all the time that were undiscovered until the data was collected. So, for example, a situation where people would regularly build from home using network shares. Instead of 20 seconds, their build took 20 minutes. No one was aware of that. Right? So you need to be able to effectively see and understand the build performance across all usages. Without that visibility, it is impossible to achieve and maintain high build performance across your organization. A lot of money is on the table here, as well as happy developers. The latest version of Gradle Enterprise provides you more insights than ever into the performance of your builds. Luke will tell us more about this.
Thank you, Hans. All right. So what we're looking at here is a build scan. Who has seen a build scan before? Excellent. Excellent. OK, so what I'm going to show today is some of the things that you may have seen and also some new stuff, which is new in the 2017.4 release, as I mentioned, came out earlier this week. So build scans have a dedicated performance section, which really gives you a breakdown of where the time went in your build, trying to point out hotspots to you, areas that you can go and optimize to make faster. So I've just gone into the performance section here, and I have a breakdown of the total build time broken up into the higher level phases that Gradle goes through when executing a build. So you see the total build took about 7.3 seconds, a little bit more than that. The kind of bootstrapping that Gradle does here was all relatively fast. It looks pretty good. Those numbers are OK. And of course, something popping out right away here is I have a 5-second configuration time on this build, which is too high. It's all right, Stefan. You'll get to fix it. Don't worry. So right away, my colleague has sent me this build scan asking me to improve their build experience. They're not happy with this. And I can see that really what they're paying for here is a high configuration time. And I know the nature of this build. I know this seems off to me. Task execution time looks OK here, 1.5 seconds. I think we'd be happy if our build's completed in 1.5 seconds in terms of the real work. And what I can also see here is some information about memory usage during the build. So I can see how much time was spent doing garbage collection during this build. In this case, it was negligible, almost 0, which is good. And I can also see information about a heap memory usage. So what we're seeing here is each of the heap memory pools, what was the peak usage during the build for them. So that's going to point out to me if there's memory constrained. If I see these numbers reaching the max along with a high garbage collection time, then obviously this build is starving for memory. If you see that these numbers are relatively low and this garbage collection number is also high, then it may indicate that you're over allocating and you're having large garbage collection sweeps during that. So this can point to memory allocation problems as part of performance. So moving on, the project configuration section breaks down that configuration time by project or evaluation of each project during that. So right away here, and this is ordered by slowest first. So what were the slowest parts? And you can see the root project was actually dominating here. And also interestingly, I can see that one of the child projects is poking out here as well. So something's going on configuring this child 7 project that is making it much slower. It's taking a second. Or you might seem like a second's not a long time, but in terms of project configuration, all these numbers should be very, very, very low. So this is actually an eternity here. So we can drill in a little bit further. So this is what happened while we were evaluating the root project. And here it's broken down by the scripts and plugins that got applied during this time. So here's the root build.gradle. Here's that project's build script. And we can see that it took nearly 2.99 seconds, which again is quite an eternity. I have two numbers here. This is the total time it took to execute that script, including all of the things that it included, because your build scripts will pull in other plugins and other scripts. So that's the total time. This number here is the time spent just in that script. So this is pointing out that that script itself is doing something that is very slow, not something that it's applying, which is very useful information. And I can also see here that I have a script plugin off on the side, which is taking a second. So that's something that's not right, obviously, there. So I can now go and look at that script and see what is it doing. It's likely calling out to some network service or doing something slow, or it has some kind of a hot loop or something in there. So it's now pointed me, I can go and spend some time in there making that better. That's going to get my build time down. Moving on to the dependency resolution. So a similar kind of idea here, but breaking down the dependency resolution events by time. You see how much time was spent resolving dependencies altogether. And right away, this is pointing out the problem to me right here. So I've got a significant dependency resolution event happening during project configuration here, which is eating a lot of my time. I can even see which that is. The task execution section, I'm going to, for the sake of time, kind of skip over this. Etienne will cover this a little bit more when he talks about it, but it's a similar idea. Breaking down the tasks that were executed, show me the slowest first. I can see a breakdown of the different kinds of outcomes, what was the time for the task that was skipped, the tasks that were up to date, etc. The build cache tab. So this build did use the build cache, and I can see which caches it used. It used a local build cache. It was configured to push to that cache. Particularly if you have multiple caches or multiple remote caches, or some build cache configuration that may be a little bit smart, kind of switching things on and off in different environments, it'd be very useful to know exactly what caching was effective for this build. And I see a breakdown of what were the cache operations. So in this case, we had 4 tasks that executed, and they all missed from the cache. So that took a very short amount of time, and I can see the write-backs to the cache here, the store operations, how long they took, and what was the effective data transfer rate to do that. So for a local cache, that's not so interesting. You're really constrained by disk here. But for a remote cache, this is particularly interesting. So if you see a low number here, that's going to tell you that your network is constraining your performance here, and the time it's taking to either fetch or store to that remote cache. So that's the total summary. I can also see that same information for each operation. So these are the tasks that use the cache. This is the cache key. How long did that load or store operation take? And again, what was the effective transfer rate? How big was the artifact? How many entries were inside it? Just as an indicator of the complexity of the operation. The time it takes to do certain things, if there's a high entry count within the artifact, may impact there. And I'll talk more about that in the Gradle Enterprise talk, and I imagine the build cache guys will as well. I can also, so another thing I'd want to know if a colleague sent me this build scan asking about the performance is, what was the daemon situation? Are they running with a cold daemon, or is it warm? Because having a warm daemon is really key to performance. And there can be some reasons why the person's not using the daemon. There may be some configuration issue which is causing the daemon to thrash and create a new one each time or something like that. But I can see here that this daemon had been running for 10 minutes before this build was run, and 4 builds had run before. So that's enough time for things to get warm. I can also see the actual network activity that happened during the build with regard to dependency resolution. So here I can see that 3 files were actually downloaded, the total number of bytes that were downloaded, how much time was spent on that, and the speed here. Now my situation, in particular, I've looked at many builds, and I've got a good feel for what's going on here. I can look at these numbers and think, well, those transfer rates really aren't what they should be. So that's telling me that the speed between this person running the build, wherever they are, and the repository is an issue, or the throughput there. Another question would be why things being downloaded at all, if this should be warm, of course. And finally, there is a settings and suggestions section here to talk about, to kind of point out some different things that you may want to look at. So it tells us that daemon was on, parallel was on, etc. I'm using an early version of Gradle here, which it's giving me a little warning about, but that's okay. It's explicitly telling me about the problem that I had, that dependencies were being resolved during configuration here, and also telling me that some of the tasks that I ran weren't cacheable, so perhaps that's something I want to go and look at. And just to wrap it off, we saw that execution time wasn't really a problem in this build. It was being dominated by configuration time. But if it was task execution time, this graphical timeline of task execution may help indicate what the problems were. In this case, the build is being dominated by test time, which is a reasonable situation, often one of the slowest parts of your build. So we're OK here. So that was just a quick overview of some of the performance aspects of build scans. We'll go into some of those in more detail, and Etienne will also cover some other scenarios. So, thank you.
I will talk later about the professionalization of our domain. Right now, I want to add one additional perspective here, right, on the effect of build performance. So when you look at the scale of LinkedIn, where are the LinkedIn folks? So we're talking about 300,000 Gradle builds per day overall in the organization, 200,000, 300,000?
300,000 per week?
I thought. Per week. And including local builds. What's the last number?
Excluding local.
OK, so anyhow. Having 300,000 builds, right, and making them 1 second faster means 300,000 seconds faster feedback, right? That is 83 hours, which is 10 engineering days of faster feedback, right? By 1 second faster build, right? So the more you build, right, we now still at a point we're talking about minutes, 20 minutes, right? But I think, right, at scale, we want to come to a point where we're saying 1 second is serious money for LinkedIn, right? It's worth to invest into that, right? That is where I see, at least at scale, our industry to develop, that a second counts. Not because anyone is complaining, but because the ROI is worth it to invest into that. So what happened here? We haven't yet talked about how to understand trends with the data you collect with Gradle Enterprise. There's a company in Seattle who's using Gradle and Gradle Enterprise, and they also sell a damn good tool to visualize trends. So what else would they do than to connect their tool with Gradle Enterprise to improve their developer productivity? Please welcome Sam Snyder from Tableau.
Hello, everyone. It's very exciting for me to be here with you today amongst my fellow builders of software. At Tableau, we've been trialing Gradle Enterprise for a while. But before we even get to that point, Tableau is a company whose mission is to help people see and understand their data. And through seeing and understanding that data, gaining insights that you wouldn't have had otherwise. And with those insights, making better decisions for your business, for your scientific endeavor, for your builds. But it took us, it was a long road for us to even get this far. Back in the day, we had a Ant and Ivy build that took us forever. It was homegrown. And we got together and converted it into a Gradle-based build where we immediately saw very impressive performance gains, like some of the charts Hans has been showing you comparing to Maven builds were all definitely true of our Ivy builds, and then more so. But achieving those new efficiencies, achieving that higher performance, part of the effect that had was showing us how long the long tail of problems with our build really was, how after this core inefficiency was removed, there were hundreds of issues, and we struggled to prioritize them, to deal with them effectively. Was problem A really a problem for a lot of people or just the one person who ran into it? Was issue B incredibly severe or relatively trivial? Amongst a field of bugs and problems, our own product's capacity to help us consume and make sense of complexity wasn't helping us. And this was confusing and frightening until we went and looked into it more and saw that the reason a capacity for complexity was doing no good was that our data wasn't complex. All of the telemetry, all of the information we had on our build systems was outright simplistic. So it did not record the build in a debuggable level of detail that would let us optimize for performance, that would let us address those critical reliability issues that were costing me and all of my friends and colleagues considerable pain, considerable lost productivity. Until Gradle came out with Gradle Enterprise. So as soon as I heard about Gradle Enterprise and heard about build scans, I arranged and set up a trial. I went to some of my best friends and I volunteered them to participate and to send me all of their build information. And after only a few short weeks, I was able to begin to bring that information into Tableau, and the patterns and insights that were obfuscated to me before suddenly started to become apparent in front of me. We could see where the bottleneck was and measure how much time, how much developer productivity would be earned, would be gained back from addressing that bottleneck. One such performance optimization we've been hearing a lot about so far, the Gradle Enterprise build cache. So over here I have Tableau hooked up to my Gradle Enterprise data, and I have charted in a few places our cache hit rate. To try and see, okay, we turned this on. Did it do anything good for anyone? Like, does it work? And you can kind of see at this is the x-axis is weeks. And so you can kind of see how long my trial has been running. This is the point where the yellow area is successful task executions. The blue area is cache hits. So you can see when I turned on the local build cache, most developers would see a few cache hits, and that's nice, but it didn't really kick into high gear until I got our continuous integration servers publishing to the remote cache. So over here in these most recent 2 weeks, could see that our cache hit rate, now represented by this blue line, jumped up to be actually a majority of all Java compiled tasks result in a cache hit now. We achieved, without any deliberate optimization beyond just turning it on, a 70% cache hit rate, which, that's cool. Does that actually save time? Like, if hitting the cache were slower or not substantially faster than actually executing the task, that wouldn't really matter. That wouldn't help. So the next step is to try and tell how much time it actually saved people in my trial, represented by this block here. And even though my trial is only maybe 40 active developers, in that first week, amongst about 40 people, almost 24 hours of time were saved based on my estimate of the average cache hit duration versus the average successful task execution duration. So, everyone saved, every single person saved like a half hour, right? I'm very excited to roll this out to more people in our organization, as over the course of weeks, this will be getting us back entire days of developer productivity for every single person. So this is fantastically exciting as a performance optimization. Another key area, in addition to how fast the build is how reliable it is. And as I talked about before, we had this big set of problems that were difficult to prioritize, difficult to see the incidence rate, to tell how many people were affected, aside from going into the hip chat rooms and listening for the wailing and gnashing of teeth. So now, when it comes time for bug triage, we have this handy failures dashboard, which I can sort by time. And so I can see right now it's set to the past 2 weeks, and each of these colors represents a type of task. So we see that some of our TypeScript projects are areas of consternation at the moment. And beyond that, we have some copy tasks that occasionally fail, and we have some symlink creation tasks that fail. And if we want to dig into these, I have this dashboard set up to give us links to all of the build scans that ended up comprising that block. And let's see if my VPN connection back to work is holding strong. It actually is. So I can go and investigate the build scans that I've been showing you directly from this dashboard. this has already, in a very short period of time, been invaluable to us during triage time, as it's no longer a guess as to what is causing my friends and colleagues pain. We can now see it before us in brilliant color and have the next steps of where to dig in laid out before us. This is extremely exciting to me, as now I have the power that I try and sell people as someone who works at Tableau, of using data to make better decisions. And I can use it to help my friends and me, I mean, I do a lot of building, to help the friends and colleagues who I really like working with to be really effective in their day so they can advance that mission to help people see and understand their data more effectively. We've just kind of scratched the surface here, but I will be giving a longer talk on this subject, which I believe is in this room later today. So those of you who are interested in this subject, I welcome you to come join me, and we will dive into some of these things in a little bit more detail, and I will show all of you how to set this up for yourself, how to connect Tableau or whatever other visualization system you may unfortunately be stuck with to Gradle Enterprise to get some of these insights and advantages for your own organization. Thank you very much, Hans and Gradle, for having me here today. It's been a pleasure. Thank you, Hans.
Yeah, I'm not sure about you. I've seen the future.
I heard that if you just
And
hold the laptop.
demo already moved the focus to the next pillar of build performance, which is build reliability. Without build reliability, all the performance achievements are worth not that much. So what to do to achieve build reliability? First of all, the build platform itself has to be as reliable as it gets. As you've learned, the new Worker API will make parallel execution not just more efficient, but also more reliable. So reliable that we will enable it by default. The build cache has enhanced the Gradle input-output model to model task input-output more precisely. And the cache is also a forcing function. When we made the Gradle Java tasks cacheable, we run into corner cases we had to fix. Because if you really, if this has to work with clean builds, right? This has to be 100% reliable. As a side effect, running the Java task now incrementally is also very reliable. Making your custom task cacheable will have a similar effect. One open issue we still have in this area is configure on demand, which can be misconfigured. Our work on making configuration times faster will get rid of this workaround and will enable this behavior reliably by default. Similar to maximum build performance, though, the reliability of just the build tool is not enough. Gradle has 1,500 plus constantly evolving community plugins, and you want to be agile and aggressively and continuously roll out your custom build logic improvements to make your developers more productive. Your build logic will have bugs. The community plugins will have bugs. If your developers start doubting the correctness of the build, they will do weird stuff. No. They will always do clean builds, disabling incrementalness. That's the start, right? They will create aliases for always calling refresh dependencies when calling Gradle. We've seen that, right? They will send around scripts that delete every hidden Gradle directory on a machine, and they might disable the build cache. Debugging code issues for them is already hard enough. Every additional dimension that introduces uncertainty is deeply stressful for developers. And because of that, they easily get paranoid, right? And are very receptive to fear, uncertainty, and doubt. Rumors about the build. So they'd rather waste hour after hour in build time than to have another dimension of uncertainty. How can we fix that? Similar to the performance aspects, Gradle Enterprise empowers you also when it comes to build reliability and build logic debugging. Every build and flaky event is captured. You can use this data for preemptive analysis, as we have seen, and any build issue can also easily be reported by developers and analyzed in depth. If there has been a real issue, it can be confirmed without the need to reproduce, which is often hard. If there wasn't a real issue, it can be proven to the developer that there was a misunderstanding. Both will establish trust into the build infrastructure. Etienne will show this in action.
Good morning. Builds happen in succession, and so it's really helpful to understand how those builds evolved over time. And we currently have two views that allow you to understand the bigger context of a single scan. One is the scan list. So here we can use ordering and filtering to narrow down the builds we want to see and reason about outliers, trends, and so on. So of all the builds that have been published and that we see on the scan list, so all the scans that are in the system, I can filter. For example, I'm filtering here for a project, and I only want to see those that ran a certain task, which is the assemble task. I can now see I have like 25 builds, as you can see down there, and I can check how many of those actually failed. So we have like 10 failures in here, which gives me a ratio of good builds versus bad builds. I can also search just for the successful builds and order by duration. And I can now use that information to better understand what is the fluctuation in execution time of the build, and so on. The other way to get a bigger context of a single build scan is the navigation feature we have on a single build scan. Here I can navigate back and forward in time. I can do so on two levels. One is the user level and one is the workspace level. Workspace level means every build that runs with the same .gradle folder in my project root is associated with each other. And the other one, the user level, is every build run with the same Gradle user home is associated. So if I run a lot of builds locally, I can navigate back and forward as a developer between the build I ran previously for the same project. On a CI agent, typically you run multiple projects. And so you want to navigate back and forward in time across all builds, no matter from which project they were. Because oftentimes a build is affected by a build that did something previously. Maybe it left over some things that then affect negatively the next build. So these are the two levels of navigation that we provide. So I can go back and forward here with previous, or I can go forward. I can also use it to compare builds. A scenario we probably all have had is that you're running a task and it's executed, but you're not really understanding why. And you're doubting whether it's a Gradle issue or whether it's an issue with your task. And it's almost never a Gradle issue, but you still want to get that confirmed. Right. So what we provide you now is on the task view, we give you a little task details pop-up where you see exactly the reason why a task was executed. Right. To give you another example here, that task, the jar task was executed, and we can see from the output or from what's reported that is that the output file actually changed. In this case, it was removed. Right. So we get a lot of confidence in what's happening in Gradle because we can see why something happened. We don't have to do guesses anymore. If you're using the build cache, task inputs and outputs are essential. And we expect that if the task inputs are the same, we always get the same output. And tasks with the same input, when the build cache is enabled, can share their outputs. One can put it there, and the other downstream can consume it. But what you might observe is when you run this is that one task puts it in there, and you can see this in this screen. You can see there's this cache store into the local cache. You run another build 10 minutes later. This was run at 6:38. I'm running another one 10 minutes later, different machine, different user. And I expect now to be the cache, the task output that was put into the cache to be reused. But it's not happening. We see again that we have a cache store. And that is something you will observe when you use the build cache. So the question is, why did it not reuse the task outputs? Something must have been different in the inputs. Right? And what we provide to answer that question is a task inputs comparison view. So here we take two builds, and for each of the same task, we give you the differences in inputs. And what we can see for those two builds that I just showed you is that there is actually a change in inputs. So there's an input property called username that did change between those two builds. Okay, armed with that information, we can now decide, well, does it even make sense to have that input property username on that task? Or if yes, does it make sense that the value is different or not? But that is then the next step. At least we now understand what caused the differences in inputs. Another example, because we can do more than inputs, we can also tell you if the implementation of do first or do last changed, or if the class path changed of that task, and so on. And that's all visualized in the task inputs comparison for each task. Sometimes the opposite can happen, is that a task is reusing an output from the cache, but it shouldn't. You're like, that shouldn't be the case. So what we provide for that inverse scenario is that if you go to the task that consumes the output, you can see that here with the cache hit. Sorry, down here, it has a cache hit. You can navigate to the task that put that artifact into the cache. So super powerful feature to go to the source that put it into the cache. The same works for incremental builds, so not only for cache-enabled builds. If you want to make your performance faster, you first need to understand where performance or where time is spent. And on the timeline, you can see where time is spent during the task execution phase. And you can see visually at the top how things are executed one after another and in parallel, and if things can be made more parallel. You can also search or display in duration order. So we can see what tasks took the longest, because those are the candidates to improve, because the faster the task, of course, the faster the build. What we can also do is we can search and say, well, all the tasks that executed successfully, which ones were not cacheable? And you can again see which ones those are. And those are, of course, now candidates to make cacheables to improve the performance. We can also ask the reverse question, which is, which tasks were cacheable but still executed? Because that could point me that maybe I have my pipeline not set up properly, such that the build that puts the stuff in the cache is first, and then the consumers are next or later. Maybe I have this set up wrong way. Right, so you can do all these experiments with this view. Often a candidate of problems can be plugins, external plugins, internal plugins. So understanding all the plugins applied to my build is very useful. And for that, we provide a plugins view. And if you think about it, there's no way in Gradle on the command line to get this information of all plugins for all projects. So here we can also search, like on most views. I can say, I suspect my build failed because of the shadow plugin. Something went wrong there. I can search, I can see in which project is it applied. And I can also see the version, 1, 2, 3. Well, there's a 2.0 out, so maybe that caused the issue. And I can take it from here. Last thing to show, we talked a lot about build failures. And we can see here all builds, and I can say, just show me the ones that failed, for Wrap-Packed in that case. And I see 35 builds failed in the lower right corner. But it would be nice to qualify better what are those build failures. Some are test failures, others are dependency resolution failures, totally different category. So what we can do is we can categorize those failures, and we can use that. We can do that using custom values, and we can have our own category system that we want. So in this case, what I did is I tag every build that has a test task failure with a certain task, and now I can just search for those builds. So I can say, give me all builds with the task test failure. And now I can see 4. So 4 out of the 35 were actual application logic problems, while all the other ones were build issues. And now I can, of course, go and optimize this and say, well, of all of those that were not test failures, let's split them up more so I know which ones were failure because I put in a wrong task that didn't exist or anything else. Right. With that, I hand back to Hans.
So everything is happening fast and reliably now, right? Everything? There's still so much activity that developers have to do manually. Gradle is a generic, very extendable automation tool. One thing that will help you tremendously to automate more is our plugin ecosystem. I already mentioned that. But there are workflows that need modeling deep within Gradle to support and automate them. For example, if the builds for your separate code repositories are very fast, that's great. But if it requires a lot of manual setup work to work on multiple code repositories at the same time, the degree of automation is not what it should be, and you are wasting a lot of time and focus of your developers. One of the highlights of the Gradle Summit 2016 was the composite build feature that addresses this problem. Many organizations have started using this. We have added new capabilities to composite builds, and that's what I want to talk about. So composite builds work now with the continuous build feature. By the way, the continuous build feature is a hidden gem. With all the performance improvements, it is more valuable than ever. If you haven't done so yet, check it out. The IDE integration for composite builds is excellent now. We have invested a lot of time to integrate composite builds with the tooling API. Especially the IntelliJ integration has much improved because of that. Some of the work to run composite builds in parallel by default is already in master. It will be production ready in Gradle 4.2. On the roadmap, we have features high on the list, integration with build scans when you have composite builds. We want to make the substitution more configurable, and we want to allow you to address task names in composites directly from the command line. One other feature that is available in Gradle 4.0 is variant-aware dependency management. It is still mostly an under-the-hood feature at this point. The Android plugin is making heavy use of it, and as I've mentioned, the feature is an enabler for good Android performance. But it is much more than that. It is a key feature to describe and automate workflows much better when it comes to dependencies. Adam will explain this feature to us.
I want to start with looking at some problems that happen or can happen when you do something like this. And then we can look at how variant-aware dependency management can help solve these problems. So I've got a dependency on some library project. So this looks pretty reasonable. We do this all the time. What are the problems? So there's a class of problems that comes about because Gradle assumes that for every dependency, for each dependency, you only ever want one set of files from that dependency, and you only ever want one set of transitive dependencies. So what that means is, as a plugin author, I have to make a decision. When I'm producing some library, what will that one set of files be that I'm going to expose to consuming projects? And what will that one set of dependencies be? So let's take a look. So let's say I'm producing a Java library. Which file do I give to my consumers? Probably the jar. It's got all my classes in it. And dependencies, well, depends what they're doing, but I guess I have to give you the runtime dependencies because that's generally the superset of all the things my library needs. What if I want to provide just the API classes for my library at compile time and just the API dependencies for my library? So given the assumption that Gradle has, I can't do that. I've got to choose either compile stuff, which obviously doesn't work at runtime, or runtime stuff, which obviously is leaking all this extra stuff, all my implementation details. What if I want to produce a Java 8 version of my library and a Java 9 version of my library? Which one do I give you? If I give you Java 9, it's not going to work on Java 8. If I give you the Java 8 version, it's probably not going to work on Java 9 if I'm fully gone with Jigsaw and modules. So do I give you both of them, let you choose? What about if I want to produce a shaded and an unshaded version of my library? Which dependencies do I give you? They're different in those two cases. What about test fixtures or source files or Java doc? test reports, IDE configuration files, all this stuff. Basically, you can't do it with this assumption that Gradle makes. You know, there are workarounds, hacks you can do, but it gets complicated very quickly. So what about an Android library? So which files do I give you for an Android library? I don't really know what you're going to be doing with this library, but probably building some stuff against it, I guess. So I'll give you everything. But I don't always need everything from the library. Let's say I just want to produce my application's manifest. I have to wait while Gradle builds all of these different pieces of the library, all the resources and the manifest and the assets and the classes and the native libraries and all of these other things, zips all this stuff up into an AAR, and then immediately unzips it so that I can reach in and get the thing I need. So lots of extra work going on here that I don't need. So this isn't good for performance at all. But it has a serious implication having to do this, in that now I can't actually build anything in parallel. So I can't build any pieces of my application until I've built all of the pieces of my library. So if I just want the manifest, I have to wait until everything's been built. I can't start generating the application's manifest as soon as the library's manifest is available. And I can't start generating the resources for my application as soon as the library's resources are ready. So this just kills performance for Android builds. And this is one of the major reasons why we've introduced variant-aware dependency management, is to just get rid of those performance issues. So what about C++? Which files do I give you and which dependencies? Well, who knows? If I give you the Windows binaries, that's not going to work if you're building for Linux. Do I give you the optimized binaries or the debuggable binaries? Do I give you stuff built for pthreads? Which standard C++ library are you using? You just can't there is no answer to this question, essentially. I could give you everything, but then we're back where we started with performance. And that also assumes that I can actually build everything and produce a single a single thing. Oh, that's the answer. So what Gradle lets you do now is a plugin author can define multiple sets of files and dependencies for Gradle to give to consuming projects instead of one. And each of these is called a variant. And then associated with each variant is also some metadata that describes what that variant contains and what it's intended to be used for. And then on the consuming side, what a plugin can do is it can attach metadata to dependency configurations to say what they're intended to be used for, and Gradle can connect the pieces. So that for a particular dependency, Gradle can give you the right variant based on what it is you're doing at any given time. So that means when I'm compiling my Java, Gradle can give me the API classes and the API dependencies. I don't need to leak any of my implementation details. When I'm building for Android, Gradle can give me a variant that contains just the files I need. So it's not doing all this extra work, and I can do stuff in parallel. So if I'm producing my application manifest here, Gradle can give that task a variant that contains just the library's manifest and nothing else. And so as soon as that's ready, Gradle can start building that piece of the application while it's continuing on building the other pieces of the library. And then for native, Gradle can give you the right binaries at the right times. So this is available now. It works for between projects in a multi-project build. So if you're using the Java library plugin, or even if you're using the Java plugin, you're using this now. So this is the Java plugin is using variant-aware dependency management to implement the API implementation dependency separation. If you're using the Android 3 alpha, whatever we're up to, 4 or so, plugin, you're also using that. That makes heavy use of variant-aware dependency management. It works for composite builds. So something it doesn't work with yet is when you're publishing to a repository, a binary repository. And this is what we're working on now, is making it possible for Gradle to take all that variant information, publish it to a Maven repository, and when you resolve it, Gradle uses the right files at the right times. So that's a very quick introduction to variant-aware dependency management. Thank you.
Yeah, so let's talk about the roadmap in this area. There's one feature scheduled for Q3, in this area I mean higher degree of automation. There's one feature scheduled for Q3, Q4, where just the thought that we will have that soon brings me joy. We call this feature source dependencies. This will allow you to declare source repositories as a dependency. For example, a GitHub URL. You can use this to declare a dependency in the dependency block, as well as to declare a composite. This will be a huge progress when it comes to automating developer NCI workflows in multi-repo environments. We will do this as part of our upcoming Swift support, as the Swift package manager is also based on source dependencies. For Swift support, we will initially focus on Swift on the server side, but it will also be a big step towards Gradle core support for iOS, which would be a significant horizontal increase of what you can automate with Gradle. Yeah, one feature, Adam talked about it. It's not scheduled yet, right? But we hope we will be able to deliver this in 2017. It's variant-aware dependency management that works not just within multi-project builds, but also within with binary repositories. The third pillar of developer productivity. And by the way, we started the keynote later, so and some of the demos took a bit longer, so we will go a little bit over time. One of the big time sinks for developers is the time spent on debugging. Obviously, this is a truly complex set of problems, and a solution has many dimensions. We talked already about build flakiness as a dimension we want to remove, but debugging is mostly caused by code issues, obviously. Gradle Enterprise has valuable data and features to easily and quickly remove additional dimensions in the exclusion game debugging often is. Etienne will tell us more about that.
So when we work with builds, the console is a key source that we consult. We may look at it if things go well, but also when things don't go well. And you run your build, it behaves not as you want to. You take a look at the log, which we fully capture in build scans. You might see something like in this example, which doesn't make much sense, and you're kind of out of your depth what to do about it. So you're going to share with somebody who knows how to fix it. And so with build scans, everything is very linkable. So I can just select that line, and I can use that URL, share with somebody else, and we can look together at the log, or they can look at it on their own. Right? We also can look at the log when we have failures. So we have a JavaDoc error that happened, and we're not really sure what to do about it. We can select those lines again and share it with somebody else. Now, interesting about this example is that when I ran it on another machine, it worked. So weird error. Maybe it could be related to the JDK version or not. So let's take a look at the build comparison. And here we can compare two builds. In this case, we compare the infrastructure before I showed the task inputs. And there we can see that there is a difference in the version being used. So we see on one is 131, and in one it's 102. So this is a strong indication that this might be a problem. Right. And I didn't need to consult anybody else to figure this out. As a developer, I was able to resolve this on my own. For those that run tests, of course, you want to see the tests that fail, the tests that pass, and especially for those that fail, you want to see the whole output of what happened. So with build scans, I can go to a test that failed. The whole output is captured, and I can now reason about the failure. Or I can share with somebody else if I don't understand what's going on. Right. I can also take a look at all the tests in the system. Yeah, the resolution is, this is too big here. And I can see them sorted by duration, and I can try to make the slowest tests fastest. Right. This is often a very low-hanging fruit to make my build overall faster. Dependencies. Every project has dependencies. And in Gradle build scans, we capture all the dependencies of all projects in a unified view. Right? So different to Gradle command line, where it's per project, it's across all projects. And so here I can see all the dependencies, all configurations nested as much as needed. I can also search for dependencies. So let's say search if this project uses Guava, and I can see, okay, yes, there is Guava in use. I can also see the version being used. I can go and look at more details down here, and I can see what is it depending on and who depends on it. Right? We can also take two builds and compare them with respect to dependencies. In this case, I ran the build with RC1 of Wrappack and then RC2 of Wrappack, and I can see easily, oh, some dependencies have changed in version. Right? It could also be that some dependencies are new. We would also display them, or they have been removed. And this can cause, especially when you have a lot of dependencies changes, it could cause something doesn't compile anymore, and so on. So it gives you another data point to understand why something doesn't work anymore when it worked before. Right. Build scans capture a lot of stuff, but there's never everything that we can capture. There will always be stuff that you would like to capture that we don't, and you can. You can capture anything you want to, and we will display it in the build scans, and you don't even have to pay extra for that. The way we do this is with custom values, custom links, and custom tags. And I'll give you a few examples. Let's say you want to tag all the builds that we saw on the scan list. You want to know all the ones that are on CI versus those that are local. When I run the build, I can add some logic to my build saying, add a tag called CI if I'm running on CI. And then those tags show up here. You can see this one is a local build, so it's not a CI, it's the opposite. And I also have a tag called dirty, meaning I have some local changes. Right? That logic is my logic that I put in the build, added as a tag, displayed in the build scans. What many projects do is they have some code quality metrics in place that are run as part of the build. For example, check style. And here we see we had some check style failures. We see them as custom values. So what happened is while the build ran, I listened to check style failures in some sense, add them as custom values, and now you see them exposed here. And then you can easily fix them. Another thing we are often interested in is the state of our sources. Especially when we start sharing a problem with others, the other person wants to understand, well, what version of the code were you on? What local changes did you have? And so we can also capture that as custom values. Maybe at some point we will capture it in a build scan plugin, but until then, you can do it yourself and with any VCS that you want to use. So here you can see we captured the branch name, or I did capture the branch name, we captured the commit ID, and we also captured the status. So I had some local changes here. So this is additional information that helps somebody else to reproduce the state I was in. And the last aspect of what we can do with those custom values is we can also integrate external reports. So if I publish some reports as part of running the build, I can then link to them. That's the current integration we have. And so I have a few examples here. With source, I can link to the exact state in Git that was used. Right. That's a custom link that I added. Another custom link I added here is to a Git gist. And what I do is at the end of the build, I collect the diff, add it as a gist to GitHub, and now link to it. So in the end, what that gives me, for each build that I run, I have a diff basically of my local source state versus the one that was committed. If you use another system, you can easily adapt that. And the last example I want to show here is, let's say you want to incorporate with a ticketing system. So you have a failed build, You want to open a ticket, maybe with the Gradle even, make that as convenient as possible. I can click on that link that I created. It takes me to the Gradle forums. Automatically creates a topic, already puts in the link to that scan. It's a bit small, but believe me. It points back to the build scan. And now I just need to add a bit of description, hit the post button, and now we have an issue where it explains what the problem is, and it points right back to the build scan where everybody can look at it and know exactly what were you doing, what was the state of the system. Right. Yes, and so to finish this, we are capturing some stuff. You can capture more stuff. But besides the aspect of just capturing information, it's a lot about sharing information. So everything is deeply linkable, whether it's a test, it's a log, it's a custom value. You can always share this with others, which makes it really easy to collaborate. And the other aspect is the historic aspect. Since we capture all the build scans, or we collect them all and keep them, you can always go back in history, compare to those builds, check what happened back then. Right. Thank you very much.
That brings me to the last pillar of productivity, culture. A very important topic. I want to keep it rather short today. So accountability on the side of the build masters and the developers. Especially larger monorepo builds need more accountability, as a single person can do a lot of damage that affects everyone in terms of reliability and in terms of performance. We need accountability for both the build team and the developers. Both have a lot of leverage to introduce changes that affect productivity negatively. By bad build logic, by slow tests, by introducing frameworks and languages where the tooling that comes with them is very slow. It cannot be the case that developers change the build in ways that make it slow and then blame the build team that the build is slow. But we see this all the time. So that is ridiculous, and this is not mean behavior by developers, usually. It is just a complete lack of insight into those builds and a lack of data that provides root cause analysis. Gradle Enterprise can completely change that, and you can understand the effect of your changes and can reason about it versus the build is slow. Right? So I think that is the key improvement we need in our organizations to achieve high productivity. Modeling the software manufacturing process is complex, more complex than most business domains. It requires strong engineers with a deep passion for the domain to be successful. In all other industries, you have process engineers, chemical engineers, automation engineers. Those are all university degrees and very respected professions. Everyone understands how pivotal those people are, and everyone understands that they have a challenging job that requires deep skills to do it well. Software is the most complex engineering artifact of all, and here we are, the build guys. Our industry and every developer has to understand that to successfully ship software, you need very capable experts. In smaller teams, that doesn't need to be a full-time role, but it's still an important role. Without that respect for that profession and understanding how important it is, it will be hard to find and maintain the people to solve those challenging problems that we are having in this area. Gradle Enterprise helps with that as it supports you with data that proves the impact you are having on the business. So for example, the build didn't get much faster, so you don't get much credit. But when you can show, well, our code base has grown by 80%, and the build didn't get much faster, you might give us some credit, guys, because we saved you millions of dollars, right? So finally, the main job of your build team should be to create a product that makes your developers productive, that models the specific needs of your business. Jens will talk about this tomorrow in his keynote, how developer productivity teams should develop a product mindset and not just be driven by issues escalated by developers. And you created part of that product with Tableau, Sam, right? And there are many dimensions to this product. With that vision, you will get the right people into your team. But if then the reality is that they are getting drowned with requests like, why does the CI build has a test failure? Well, what does the build team know about that, right? So if that becomes the reality, that most of the work of the build team goes into supporting issues like that, your product will get postponed into the future and you're just doing emergency work, and your team will burn out and lose the passion for really creating something that makes a difference. Again, Gradle Enterprise is key to create bandwidth for your team to work on the product by either self-serving developers in figuring out those problems or by making it much more efficient to help in those cases. There's one other secret ingredient you need to be successful: the right people. It is hard to find good expertise in our space, so we at Gradle have started a professional services partner program with hand-picked consultancies that are able to deliver the quality you need. Two consultancies we know for a long time are part of this program, OCI and Some Global. Both have booths here at the conference. Talk with them and learn what they can do for you. The last section of this keynote is about features that improve the developer experience when using Gradle. Last week, we fully launched the Gradle Guides at guides.gradle.org. It is a goal-oriented approach to make people successful with Gradle, whatever they need to do, like building a Java library, an Android app, or web application. We have already 21 guides. Many are getting started guides, so that people don't have to getting started with an 80-chapter user guide. But they are also in-depth expert guides, for example, on the build cache, right, which is a must-read for anyone who wants to use the cache seriously. There are more guides to come, and hopefully also from you, our community. The whole guide infrastructure is designed for contribution. We have a guide on how to write a guide. Every guide has its own GitHub repository and gets published from there, so it's very easy to get started and to contribute. So if you are a plugin author, a guide will give more exposure to your plugin. If you are an experienced Gradle user, it will be a very prominent place to share your knowledge. Ken Cousin is here, one of the implementers of the new guide section. If you have any questions, reach out to him. Ken, where are you? No. Improving the documentation has been high on our list. There's still a lot of work to do, but this is great progress. Everyone at Gradle loves the new console. Eric, who's driving this effort, will share more details.
No fire alarms, please. This year, Hans established performance improvements as a top priority for the Gradle build tool. We soon realized that increasing parallelism would present challenges and opportunities for the Gradle command line experience. This is the experience for Gradle 3.4 and before. As you can see, only one item is shown for what's currently being executed. Parallel work competes for display. Similarly, logs from parallel task execution are interleaved. This is especially important to address as we introduce more parallelism by default, as Gary just showed. Finally, many large builds' log output is unusable with the amount of default logging. So we got to work, focusing on 4 primary things. First, a visual persistent build status to quickly answer, will my build finish soon or later? Parallel work in progress display to answer, what is Gradle doing right now, with more granular information so you can feel Gradle performance. Grouping logs by the task that generated them, no more guessing where those warnings are coming from. And finally, a terser but more informative build summary that gives a sense of how Gradle achieved the requested tasks. Along the way, we've also polished things like continuous build and other things. But we're not done yet. In the short term, we will want to show you tests executed in parallel and improve handling for nested builds like build source and composite builds. Now, apart from the Gradle console, there was one more area of innovation this past year. I sought to improve the experience before Gradle is executed, and I was frustrated with the slowness and lack of features of existing Gradle tab completion scripts. After all, what is the use of tab completion if it's not as fast as human thought? Let's go back 1 second. I would like to introduce you to the official Gradle completion on this command line. It handles flags, built-in Gradle properties, and of course, tasks. Here's a demo. It's available today at git.io/Gradle completion for Bash and Z Shell. Kotlin scripts are supported out of the box, and it's much faster than alternatives, especially for large projects. It achieves this through very fine-grained caching and shell scripting optimizations. Please try both the improved Gradle command line experience and tab completion. They're not perfect, but we aim to always be improving. So let me know what you think. My Twitter DMs are open, or you can find me on the conference Slack. I hope they help you build happiness. And with that, back to you, Hans.
People no longer need an alias for refresh dependencies, right? No, I mean, those are two features. Once you get used to them, right, to the console and to command line completion, it's like, yeah, it's hard to go back. There's one more thing, the last demo, we're all very excited about, and, well, not a demo, but the topic we're covering in the demo will have enormous impact on the Gradle developer experience. Last year at the Gradle Summit, we demoed Gradle script Kotlin version 0.1. We've made tremendous progress and are not far away from version 1.0, which will make Kotlin an official build language for Gradle. The project has been renamed to Gradle Kotlin DSL, just to avoid confusion when you hear that term. Rodrigo and Paul, the lead engineers behind our Kotlin support, will show the most prominent new features.
Thanks, Hans. So, I'm here today with my friend Paul, and in his fictional life, Paul is a developer for another company, and they have this idea, right, that the gridding marketplace is right now once again ripe for disruption, right? And they have this new app they want to distribute, if only they could automate the whole process, right? So Paul asked me to help him with that, and I also wanted to show you the improvements to the user experience we've been working on lately. So I thought, what better way to do it than doing live in front of you, right? So let's go, Paul.
Yeah, so greetings, everyone. So yeah, I have like the source code of my app, but I have no build automation for it. So I'm very glad that you're here to help me.
Sure.
I saw that you created some build.gradle.kts file for me.
Yeah, that's right. So now we have this new file in your project. That's a build script. KTS means is a Kotlin script, and Gradle KTS means is a Kotlin script that uses the Kotlin DSL to configure Gradle.
Okay, makes sense.
So I saw the source code is a Kotlin project, right?
Yeah, it is Kotlin. I know Kotlin, but I don't know Gradle.
I know, that's why I'm here, right?
Yeah.
I got you, buddy. So the first thing you probably want to do is to configure how to compile your project.
Right.
And the way we package reusable pieces of functionality in Gradle is by using plugins. So the first thing you might want to do is to declare the plugins you want to use in your project, right?
Right. Oh, I see a plugins block to add dependencies. That must be it.
That's exactly it. Yeah,
now
so
I need some...
you want to compile a Kotlin project, right? So maybe Kotlin something will be there.
Okay.
Yeah.
So I see, yeah, a Kotlin function that takes a module.
Maybe you should enable documentation so you can actually understand what's going on there.
Documentation is small.
I'm sure that's not Gradle's fault.
Okay, so it's a Kotlin JVM project. So it looks like I got everything I need. Right.
That's right.
Cool.
So if you synchronize the Gradle to window, so IntelliJ knows about your update, you should be able to now build your project.
Okay. Oh, I got tasks now. Let's build.
Wow.
Oh, it's fading. What is this? Oh, yeah. JVM name, println. They all comes from the Kotlin standard library, right?
Right. Yeah. Since your application is a Kotlin application, you have to ship the Kotlin standard library with your application, so your application requires. And so you have to tell Gradle all the dependencies your application have. And you, yeah, I guess you guessed it right.
Oh, the dependencies block. Nice.
Yeah, so what you want to do there, you want to make sure your application is compiled against the Kotlin standard lib, right? Because it's failing compilations.
Yeah. Oh, nice. Okay. And it's Kotlin, and I see the same pattern. Let's look at the documentation again. Yeah, okay. So I guess that's standard library.
Yeah, that's good. And since now you have a new dependency, right? You depend on these artifacts. You have to tell Gradle from which repositories, right? Repositories, right? You got me?
Yeah, I got you. Another block.
Yeah. So
let's use gcenter.
Mm-hmm. So now the application should compile.
So let's synchronize and run the build task. And it does work. Excellent.
Yeah, awesome. What else?
I can now compile my app, but I would like to package it to be able to ship it to users.
Sure, of course. Yeah.
How do I do that?
Yeah. I mean, it's an application, right? An application. And we add functionality by using plugins, so maybe there's something there for you.
I see. Oh yeah, there are 2 plugins.
And in case you are in doubt if that's the right thing, maybe you want to look at the docs.
Read the fine manual, right?
That's exactly right.
Okay. Oh, I see there is a link to the plugin user guide. Nice. Yeah. Okay, I can set the main class name.
Yeah, so all the Gradle core plugins now have links to their documentation, so it's easily accessible from the IDE. Right?
That's awesome.
So you want to configure the application plugin. So
yeah. Oh, I just got the application block.
Of course you did.
And the main class name. Excellent. And that's create. No typo. Add. Okay.
So now if you synchronize again, you should have more useful stuff.
All right, I got some application tasks and run. Excellent. Hello world. Sounds good.
Yeah.
Okay, now I have another requirement, which is I would like my developers to have a way to run the application, but with special arguments during development. How do I do that?
Okay, yeah, so to automate this type of processes, right, in Gradle, we write tasks, right? So we write tasks, right? Tasks, yeah.
Right, got it.
So what you do, right, to create a task is that you declare a variable to hold a task by creating a task, right? Yeah.
Okay.
That should do it. Right.
Cool.
And you should be able to configure your task now. But
nice. And I get lots of suggestions, but they are not about running my main class.
yeah, that's a feature that is coming in the next version, right? Like to read your mind. But it's, it's going to take some time.
Okay, fair enough.
So for now, you might be a little. Sorry. You might be a bit more explicit by telling Gradle exactly of which kind of task you want. So you want some type of Java execution to happen, right? So maybe you can tell that you want the Java Execution task.
Excellent.
That's right.
But I wonder how this guy is implemented.
You can just look at the source.
All right.
Just go there. It's yours. It's open source.
Excellent. So I can look at what we have here. We have like arguments, the main. Yeah, that looks perfect.
It does, doesn't it? Yeah, so another thing you might want to do there, just to make it easier, right, to find it, you might want to set the group of the task. So then you can easily find it in your toolbox. That's cool.
Okay, let's synchronize. And I get my task.
Yeah, you could run it.
Okay, it's not working. Oh, it cannot find my main class. Right, it misses a class path.
Right. You need to tell the class path. But since we already have the run task there, maybe we can just reuse the class path that is set for that task by the application plugin.
That
will
sounds
make
neat.
things easier, and we can finish the demo earlier.
Right.
So
how do I do that?
Yeah, since Kotlin is a statically typed language, you need to first bring the task into scope, right? By declaring a variable that will, by getting a new task, by getting the existing task, right, from the task container.
Get it.
And that's it. Now you have the run task into scope, and it's just a regular variable. You just use it as another variable. That's it.
Cool.
And you should be able to run it.
And it works. Okay, so I can add my special argument.
You can.
Now. Okay, and I would like my developers to just run this task by default without invoking some special incantation.
I think you know where this is going, right? So you want the default tasks to be set, right? So maybe there's something about default tasks.
Oh yeah, there is.
Right. But maybe you want to use a better name for that, right? Some task doesn't really convey
yeah, naming
all the
is
goodness
like
behind that.
Rocket science. So, can I just rename it?
Go ahead.
Okay.
It's refactoring.
Wow.
Right? So everything you expect to work will eventually work.
Excellent. Oh, I got my task now, and it works.
Of course it does.
Hello, Gradle Summit.
Hello, guys. I hope you liked it. We're going to have a session specific to the improvements to the Kotlin experience on Friday, so join us there. Thank you.
Thank you.
Thanks again to all of you for coming to the Gradle Summit. Enjoy the show. Thanks.